Hi guys, welcome back. In this video, I want to talk about modeling electrical systems with a four-step approach. For this example, I pick an RL series circuit. Let's get into it. So, step one is listing the elements in the system. So, elements in terms of inertia, stiffness, friction, also the sources, and the number of ODEs. Okay, so if you guys remember, in electrical systems, our inertia elements was the inductor. We have only one inductor in this system, and we show it here. Our stiffness elements were the capacitors. Unfortunately, in this system, we do not have a capacitor, so there's no capacitor. And the friction elements were the ones that kills the energy in the system. And if you look here, I have a resistor, which is going to be my friction element. The source in this system is only one source, and that's the source voltage, which I have it here as the battery. Okay, and I'm going to show it with EN. At last, it's going to be the number of ODEs. The number of ODEs in electrical systems is mandated by the number of energy storing elements. What are the energy storing elements in these systems? If you guys remember, inertia elements and stiffness elements, or the capacitors and inductors in electrical systems, were the energy storing elements. In this problem, you see that I do not have any capacitor, but I have one inductor. Because I have one inductor, I would end up with one ODE. Good. Now that we know what is in the system, let's go and find that one ODE. In step two, I'm going to go after my dynamic variables. You might ask yourself, what is a dynamic variable? Well, dynamic variable is a physical quantity or variable that I would need to use to describe the dynamics of the system with them. In electrical systems in general, we have two types of dynamic variables. First, the voltage across the capacitors. Second, the currents through the inductors. With the number of volt capacitors and inductors, we are going to end up with dynamic variables. So in this problem, you guys notice that I do not have any capacitor. So the voltage of the capacitor, or the voltage across the capacitor, is not an option for me. The only thing that I have is the current through the inductor. Let's look at this. I have IL that passes through the inductor, and also since R and L are in series, the same current passes through the resistor. So my only dynamic variable is IL. Now I can go to step three. In a step three, I would write down the ODEs that governs the dynamics of my energy storing elements. With the number of energy storing elements, by the way, those energy storing elements were your capacitors and your inductors. You're going to write down ODEs. So, write down ODEs for every energy storing element in the system. Okay. In my case, I had only one energy storing element, and that was my inductor. If you guys look, the equation for the inductor was EL equals to L I dot L. Now at this point, I want you guys to do something. I want you guys to pick another pen and label these terms as good and not good. Okay, a valid question. What is a good term? A good term is something that's either your dynamic variable or your source. Whatever that is not your dynamic variable or that's not your source is not a good term. So the idea here is substituting all the not good terms in the equation with good terms, okay? So everything else would be a not good terms, okay? So I'm gonna pick pen with the color red to label these terms. I'm gonna start with I dot L. Do you guys think that I dot L is a good term or no? Let's look at this. Is it my dynamic variable? Well, look, my dynamic variable is IL, and I dot L is the time derivative of my dynamic variable. Look at step 2. So, yes, this is a good term. How about EL? Well, EL is not my dynamic variable. It's not my input or source. So, this is not a good term. So far, I have one not good term. The next thing is L over here. Do you guys think that L is a good term or not a good term? Well, L is a parameter, is a constant number. We don't care. We move on. Okay? So, my job is rewriting EL in terms of my good terms. Once again, what are my good terms? They're my dynamic variables or my sources. So, how do I do that? Well, I would go to step 4. Step 4 is rewriting not good terms using my tools. What are my tools in electrical systems? I have 3 tools: my KVLs, my KCLs, and Ohm's law. Okay. So here's the question. Where do I start with KVLs and KCLs and Ohm's law? Okay, let's go and see what do we have in the system. From the terms that we have, from the tools that we have, KVL, KCL, and Ohm's law. Which ones are the one that we can use for this system? Well, okay, you notice that I have clearly a closed loop here. So I can write a KVL, and I do not have any node or a junction. So KCL is already out of the window. And also for Ohm's law, I have ER. Yes, I have resistor and I can use the Ohm's law. So from KVL, KCL, and Ohm's law, I can use 2 of these guys, KVL and Ohm's law. So let's go ahead and write them down here. My KVL and my Ohm's law. They are the things that are available to me. Yes? So let's go ahead and first write down KVL to see what's happening. Imagine I am walking in this direction on this circuit. Okay? If you guys remember, for KVL, we had 2 conventions. The first convention was anytime you walk in the same direction of the current and passes through RLC elements, the voltage drops. And if you walk against the direction of the current, the voltage rises. In this problem, the current direction is given to me as IL. You guys see that? Okay. And I'm walking in the same direction of the current. So across L, the voltage drops. Why? Because I'm walking in the same direction of the current. Across R, the voltage again drops. Why? Because I'm walking in the same direction of the current. So this was convention 1. Convention 2 was regarding the batteries. We said that whenever you hit the negative polarity of the battery first, the voltage rises. Whenever you hit the positive polarity of the battery first, the voltage drops. Okay, so if I walk in this direction, I would hit negative polarity of the battery first, and the voltage across the battery drops. So let me write this one. Across L, the voltage drops. So I have negative EL. Across R, the voltage drops again. I would have negative ER. And across the battery, since I hit the negative polarity of the battery first, the voltage rises. And then this is equal to 0. As simple as this. Okay? So the next thing that we can use is the Ohm's law. For the Ohm's law, let me just bring the KVL up over there. For the Ohm's law, you guys notice that we have ER, or the voltage drop across the resistor, equals to RI, the I that passes through the resistor. You notice that since L and R are in series, they share the same current. So this is going to be IL. Okay? So they are my two tools. I'm going to go back to my step 4, okay? And I'm going to write these guys. So EL, negative, negative ER, negative EN, positive EN, sorry, equals to 0. And I have ER equals to RIL. Yes? Good. Okay. So the whole idea was writing EL in terms of my good terms. Yes? Let's go ahead and find EL from the KVL equation. Yes? So I'm going to solve this equation for EL. It's going to be EN minus ER. Let's again grab the red pen and look what I have. EN is a good term. It's my input. ER, not so much. It's still not a good term. Yes. So if ER was a good term, I was done. Yes, I had good term, all of them good term on the right-hand side. I was done. So I need to right now work on ER. So I broke down the problem to smaller problems. Yes. At the beginning, it was a big problem. I had EL. Now I have ER. ER is a smaller problem. Why? Because if you look at here, you can substitute ER from the Ohm's law. Yes. So at the end, you're going to have EL equals to EN minus RIL. Yes. So let's say that this is equation 1. This is equation 2, which is the Ohm's law, substituting two in one. You will have EL equals to EN minus RIL. Now look at this. EN, is it good or not good? Well, we already established it's a good term. It's our input. How about IL? Well, absolutely good. It's our dynamic variable. Here's the question. How about R? Is it good? Is it not good? Well, the answer is R is a parameter. Again, it's a constant number. We don't care. Move on. Yes? So at this point, you guys notice that I was able to rewrite EL in terms of all good terms. I'm going to label this equation as equation 3, and let's go ahead and label the equation that governs the dynamics of the system as equation Smiley. Okay, now substitute 3 in Smiley, what do you get? Substitute 3 in a Smiley, you will get En minus R IL equals to L I dot L. Yes, guys, if you notice, all the left hand side is your EL, which is from equation 3. Yes, now look, keep the input on one side, bring all the dynamic terms to the other side, flip the sign. What do you get? En equals to L I dot L plus R I L. You're not done yet. You need to do the sanity check, yes? So, how many families do you see on the right-hand side of this guy? Well, I have only one family, and that's family of IL. How many members? 2 members, IL and IL dot. There are no sign mismatches within the family. I can safe box this equation. If you guys noticed in this equation, you are dealing with a linear system. Why? Because every term in this equation is linear. Also, it's time invariant, which means that the parameters in the system are also constant. They're not time varying. And the order of the system is only 1. Why? Because the highest order derivative is 1. Okay. So this 4-step approach is not the only way to solve these equations or to derive the dynamics of these systems. Another method, which is method 2, okay, is writing down the KVL directly, okay, and substituting the terms in KVL. So if you guys remember, from your KVL, you had negative ER, let's say negative EL, negative ER plus EN equal to 0. Yes? Now, if you look at this, instead of EL, you can have L I dot L. Instead of ER, you can have R IL. Yes? So if you substitute these terms, you will have negative L I dot L, negative R IL, plus En equal to 0. Keep the input on one side, bring all the other terms to the other side. You will have En equals to L I dot L plus R IL. Yes, and this is exactly the same equation that we had before.